This section discusses statistical inferences for two population means using independent samples. In this section, we assume that population standard deviations are equal. Let's draw independent simple random samples from two populations. Let N1 and N2 be the sample size, and x1 bar and x2 bar be sample means. We have mentioned before that in order to compare the two population means, we can check the difference of sample means, x1 bar minus x2 bar. We also discussed the sampling distribution of x1 bar minus x2 bar. The mean of the difference of sample means is mu1 minus mu2, and the standard deviation is given on the slide. One possible way to evaluate how large or small x1 bar minus x2 bar is to calculate its z-score, or the difference of sample means subtract the difference of population means divided by the standard deviation. In this lecture, we impose an assumption to make it even easier. We assume that sigma 1 equals sigma 2. It means that the population standard deviation for two populations are equal. Denote the common population standard deviation as sigma. The z-score can be written as the expression in the bottom of this slide. Of course, in practice, sigma is unknown. A naive way is to replace sigma by an estimate. How to estimate the common standard deviation, sigma, based on two samples? We can first calculate S1 and S2 as the sample standard deviation for the two samples. Even the population standard deviation are assumed to be equal. In practice, S1 and S2 may not be equal. We need to combine them together to get an estimate of sigma. The best way is to calculate an estimate for the variance first. We may want to calculate the average of the variance, because the sample size for the two samples may not be equal. Here, we essentially calculate the weighted average. Notice that N1 and N2 are the sample sizes. The notation SP square is called the pooled variance. It is the average of S1 square and S2 square weighted by its sample size subtract 1. Notice that when calculating a sample variance, the denominator is exactly the sample size subtract 1. This quantity is also called the number of degrees of freedom for the variance. So we can say that the pooled variance is the average of sample variances weighted by their degrees of freedom. The square root of the pooled variance is the pooled sample standard deviation. It is an estimate of the common population standard deviation sigma. The formula on the slide shows the pooled t-statistic. It is obtained by replacing sigma in the z-score by the pooled standard deviation. It is the statistic we needed for statistical inference. It can be regarded as a measure of how close x1 bar is from x2 bar. If both populations are normally distributed and their population standard deviations are equal, the pooled t-statistic has a t-distribution with n1 plus n2 minus 2 degrees of freedom. Why is the number of degrees of freedom n1 plus n2 minus 2? Notice that this number is exactly the denominator when calculating the pooled standard deviation. Recall that for one mean t-test and t-confidence intervals, the number of degrees of freedom is the sample size subtract 1. Here, we have two samples. The numbers of degrees of freedoms for them are n1 minus 1 and n2 minus 1, respectively. Combine them together, and we get n1 plus n2 minus 2 degrees of freedom. This slide explains the steps for pooled t-test. We assume simple random samples, independent samples, normal populations, and equal population standard deviation. The assumption simple random samples mean each sample is a simple random sample from the population. Independent samples means that the two samples are independent. The normality assumption is important. However, when the sample size is large, it does not matter that the population distribution deviates from normality. We also need to pay attention to outliers because the t-test is not robust to outliers. We have discussed many issues regarding one mean t-test before on normality and outliers. All those comments are still applicable here. There is no good way to check the assumption of the equality of population standard deviation right now. It is mainly based on our subjective judgment. For example, we can check whether the sample standard deviations are close. We can also check their box plots. We will see that in examples. The pooled t-test is used to test the hypothesis to compare two population means mu1 and mu2. The non-hypothesis is mu1 equals mu2. There are three possible alternative hypotheses. For a two-tailed test, mu1 not equal to mu2. For a left-tailed test, mu1 less than mu2. For a right-tailed test, mu1 larger than mu2. Which alternative hypothesis to use depends on the specific applications. We then need to decide on the significance level alpha. It is usually 0.05 and can also be 0.1 and 0.01 in some applications. Then compute the test statistic T0. We need first to compute the pooled standard deviation SP. Notice that in the formula, x1 bar and x2 bar are sample means. S1 and S2 are sample standard deviations, and N1 and N2 are sample sizes. We can draw a conclusion using either the critical value approach or p-value approach. Using the critical value approach, we need to find critical values. How to find critical values depends on the alternative hypothesis. For two-tailed test, there are two critical values, plus minus T alpha over 2. For left-tailed test, the critical value is negative T alpha. For the right-tailed test, the critical value is T alpha. Make sure to use the correct degrees of freedom, N1 plus N2 minus 2. If the test statistic falls in the rejection region, we reject H0. Otherwise, we do not reject H0. We can also draw a conclusion using the p-value approach. How to calculate the p-value depends on the alternative hypothesis. For a two-tailed test, the p-value is the sum of two probabilities, smaller than negative absolute value of T0 or larger than the positive absolute value of T0. For a left-tailed test, the p-value is the probability less than T0. For a right-tailed test, the p-value is the probability larger than T0. To calculate the p-value, make sure to use N1 plus N2 minus 2 degrees of freedom. If the p-value is less than the significance level alpha, we reject H0. Otherwise, we do not reject H0. Last, make sure to interpret the results of the hypothesis test. Note that the hypothesis test is exact for normal populations and is approximately correct for large samples for non-normal populations. Let's look at one example. Suppose that 35 faculty members from private institutions and 30 faculty members from public institutions are randomly and independently selected, and their salaries are shown in thousands of dollars. At the 5% significance level, Do the data provide sufficient evidence to conclude that mean salaries for faculty in private and public institutions differ? This problem asks us to compare the mean salaries of two populations, faculty in private institutions and faculty in public institutions. Let's check model assumptions. The sample sizes are 35 and 30. They are large. The major concern is whether there are any outliers. From the normal probability plots and the box plots, we cannot find any outliers. Notice that because we have two samples here, we draw one normal probability plot for one sample and one box plot for one sample. Are the population standard deviation equal? If you look at the box plot, the length of the box is roughly equal. Notice that the length of the box equals interquartile range. Of course, it is not standard deviation. However, it is also a typical measure for variation. It can suggest that the population standard deviation are roughly equal. We can calculate summary statistics from these two samples. For the first sample, the sample standard deviation is S1 equals 26.21. For the second sample, the sample standard deviation is S2 equals 23.95. The difference is 2.26. Is this difference large? Probably not. The sample means are in the magnitude of 98 and 83, and the value 2.26 is very small. Therefore, we conclude that the assumption of equal population standard deviation is satisfied. Write out the null and alternative hypothesis. The null hypothesis is mu1 equals mu2. Here, mu1 is the mean salary of faculty in private institutions, and mu2 is the mean salary of faculty in public institutions. The alternative hypothesis is mu1 not equal to mu2, because the problem only wants to tell whether the mean salaries are different. The significance level is 0.05. We first calculate the pooled standard deviation. Plug numbers to the formula. The pooled standard deviation is 25.19. The test statistic is the difference of the sample means divided by the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Do the math, and the value is 2.395. Notice that it is a two-tailed test. The significance level is 0.05. The number of degrees of freedom is n1 plus n2 minus 2 equals 63. We can draw a conclusion using either the critical value approach or the p-value approach. If using the critical value approach, the critical value have two values for a two-tailed test, plus minus t alpha over 2 equals plus minus t 0.025. We can check this value using a t-table. It is plus minus 1.998. The rejection region contains two parts, less than negative 1.998 or larger than 1.998. The test statistic is 2.395, which is larger than 1.998. It falls in the rejection region. Therefore, we reject H0. The p-value is 0.0196. We can calculate this value using Excel. It is 2 times t dot dist, negative 2.395, 63, and true. Because it is a two-tailed test, we need to multiply the probability by 2. The p-value is smaller than 0.05. Therefore, we reject H0. Both approaches lead to the rejection of H0. At the 5% significance level, the data provide sufficient evidence to conclude that a difference exists between the mean salaries of faculty in private and public institutions. We can also construct a confidence interval for the difference of population means. The assumptions are the same as those for pooled t-test. The assumptions include simple random sample, independent samples, normal population, and equal population standard deviation. In order to get a confidence interval, we first need to find the value of T alpha over 2 with n1 plus n2 minus 2 degrees of freedom. We can see that it has the same number of degrees of freedom as the pooled t-test. Recall that the confidence interval has the general form of estimate plus minus margin of error. Here, the estimate is the difference of sample means. The margin of error is T alpha over 2 times the pooled standard deviation times square root of 1 over n1 plus 1 over n2. Last, make sure to interpret the confidence interval. Note that the confidence interval is exact for normal populations and is approximately correct for large samples for non-normal populations. Let's construct a 95% confidence interval for the difference of mean salaries, mu1 minus mu2. For a 95% confidence level, alpha equals 0.05. The number of degrees of freedom is n1 plus n2 minus 2 equals 63. Using the t-table, we can find that T alpha over 2 equals T.025 equals 1.998. The 95% confidence interval for mu1 minus mu2 is therefore 98.19 minus 83.18 plus minus 1.998 times 25.19 times square root of 1 over 35 plus 1 over 30. Here, 25.19 is the pooled standard deviation. We have already calculated this number before. The confidence interval is therefore 15.01 plus minus 12.52. The margin of error is 12.52. We can be 95% confident that the mean salary of faculty in private institutions exceeds that of faculty in public institutions by somewhere between $2,049 and $27,530. Here we still have the connection between two-tailed hypothesis test and a confidence interval. At a significance level alpha, H non will be rejected if and only if the 1 minus alpha level confidence interval for mu1 minus mu2 does not contain 0. In the previous example, the 95% confidence interval for the difference of mean is 2.49 to 27.53. We can use this confidence interval to draw a conclusion about the two-tailed test at a significance level 0.05. Because this interval does not contain 0, we reject H non. One commonly asked question is why we can still use the pooled t-test and the pooled t-interval when S1 equals 26.21 and S2 equals 23.95. These two standard deviations are clearly not equal. Notice that the assumption is imposed on the population standard deviation. A sample standard deviation is close to the population standard deviation, and usually they are not exactly equal. Therefore, even when the population standard deviation are equal, their sample standard deviation may not be equal. To decide whether the population standard deviations are equal, it sounds like another hypothesis test. Yes, we can derive a hypothesis test for that, but it is beyond the scope of this course. In this course, we mainly decide whether the equality of population standard deviation is satisfied based on subjective judgment from their value and box plot.